Hey there. I'm doing a video version of the blog today because I want to show some live stuff. Just taking a break from a service call. We're having a little trouble with the portals today. Somehow some alien civilization got hooked into the lake, and so there's flooding. It's a big mess. But I want to talk about a different kind of mapping between spaces called embedding. And so I'm going to do screen sharing. And so this is intended as part 3 of a couple blog entries that I'd written, typical neural network classification versus zero shot. And this is talking about 3D. And I did a second option where I show it in operation. And included in this, we'll do the first one here. Right, so talk about how, right, we tend to, let's say we're doing image classification, and so we tend to predict, let's say we have certain classes like cat, dog, and horse, and so each of these different probabilities can be viewed as coordinates of a point in space, right? And so this is all from the previous thing where we've got like the essence of catness and of dogness and of horseness. These are so-called one-hot vectors. And then the 3 images that we just had are closer or farther away to these. And since probabilities have to add up to 1, if you do a whole bunch of different points, right, they all end up lying, and they have to be positive values. That gives you this kind of triangle shape for 3 classes. And so we have class boundaries and whatnot, right? And then, so since that's really a 2D structure, we can go back and look at things in just 2D. Right, and so you can go through this and look at it yourself, your own. But part of the idea behind this was to understand some newer terminology and things that were coming into the literature. Yeah, this is 4 classes, forms of tetrahedron. Metric-based embedding methods, right, where we see so-called contrastive losses, where you've got like points that are supposed to be similar. This is kind of a toy model that was advanced a while back by Raya Hadsall and Pardillon Lecuon's group, where similar things are supposed to attract and dissimilar things are supposed to repel if they're closer than some margin, right? And really, this is a toy model because we're talking about mapping a set of points that are kind of in one space into another space, and it's the mapping itself, the function of the mapping, that's causing these points to move. But previously in this version of this blog, so this is kind of new, I had just a static image. Well, you could rotate it around in 3D, but it was a picture of some different clusters to illustrate what forms as a result of these embedding methods based on the contrastive losses. But then I thought, well, I'll go ahead and write one, right? So this is in there, and so we can do, here we've got 5 different classes and kind of random points and a few variables, and we could train the model, and we see that if you give it a little bit of time, what we get are, right, things sort of cluster together. That is to say, things that are supposed to be like each other in terms of the color are close to each other, and then they're separated by some margins so that you can kind of tell what's supposed to be the same and what's not, right? And so that's what I had. And you think, all right, well, this is fine. What happens if we go to more classes? So now I've got 10 classes. And so if we run this again, we can see that it, it kind of works. And if you click on more options here, you can give it more time steps and hope that it does better. And I want to show you, so this is part of this third post, I added some more controls to things and some more options. So let me go back to where that was. And right now we're doing the pairwise contrastive loss, but I'm going to change it and do triplets. Watch what happens. So we'll train the model. Boom, really good clusters. All right, and this is the case with the triplets. So with the triplets, we've got some anchor point. We grab 3 points at random in this case. Anchor point, and then 2 other points, one that's supposed to be a positive example of the same class, and one that's supposed to be a negative example of a different class. And I'm saying class in the context of classification, but this doesn't have to be a classification problem. You can use it for that, which is really interesting, but it can be used for other things as well. All right, so those are the triplets. And so we can see that this works quite well let's say we do 50, and I'm kind of holding the total number of points constant here. So we'll train the model. And once again, we get 50 classes, and they're pretty well separated. The color map doesn't quite show everything as being different, but those are different things, right? Whereas if we go back to our pairwise and run that, that's just kind of, you have to readjust the margin because it's going to cause everything to push apart. But we can even do 1,000 points, and we can do a smaller margin and train this. And the attraction part works pretty well, but the tricky part is the negative examples. And this is the thing that shows up in the literature when you're looking through literature on metric learning or embedding methods. Right? Yeah, this thing is still taking its time. Whereas triplets, we regenerate these. Look at that. Yeah, pretty cool, right? Now, again, this is a toy model in the sense that this is not a neural network kind of thing. Really, the embedding, the thing that gets trained is not just points pushing away from each other, pulling each other. It is the mapping of the points, which the points could be images, like you take all the pixels of an image and you treat each pixel as a direction in a multi-dimensional space. And the extent along that direction is given by the magnitude of the color. You can do that, but it's the mapping that gets learned. Whereas here, we're kind of just treating these things. We're going with this toy model of Hatzell saying, what if these are just points with springs on them? Okay. So caveat there, I have this caution. This is only a cartoon simulation, not a neural network, but it does capture some of the dynamics. All right. And a couple different loss options that we can do. Depends on, so you'll hear about a hinge loss, which is kind of, right, the flat part is like the margin, and then depending which way you're going, it'll be linear, right, which is a constant gradient. So this is what I'm talking about, the gradient loss. Or you could have like an L2 or a squared kind of loss that's like a parabola, and then you take the gradient of that as linear. So option for you to mess around with there. Also options for normalization. A lot of times people will normalize these things as either being like some Euclidean distance away from things, so living on a sphere essentially, or a multi-dimensional variation thereof. And again, I'm doing things in 3D so we can view it, but often we're in 128, 256, 1,000 dimensions. We can do the L1, which is kind of what we had before with the probabilities where everything's on there. All right. And I used to have an option for different metrics on the space, whether you're using a Euclidean or Pythagorean distance, or much more common, you'll see people using a cosine similarity. And this is all me writing raw JavaScript, and I just didn't feel like writing out the gradients for cosine similarity and softmax and all that stuff. So in order for it to run fast in the browser, that's why it's a toy model, but hopefully it captures some of the dynamics of a full neural network system that you can play around with. All right. So yeah, we can do this, and look at that. Right. So these things, they're trying to push each other away, and they're not able to get far enough away because of this normalization. If we were to allow the whole sphere and train that up, and if we're not constraining things to stay positive all the time, we can actually let them go a little bit bigger. It kind of depends on how you want to do that normalization. The way I've got it right now, if you let this thing go, they will eventually fill the sphere. Okay. So yeah, so how does this relate? Well, right now I'm just choosing the negative examples at random. And this is okay in 3D. As we go to higher and higher dimensions, it turns out that you're more likely to have points that are far away, that are beyond the margin from a given point. And when that happens, the model learns nothing from those examples. And so a lot of the work in metric learning I've been learning is about how to choose those negative examples well, because if you're wasting time choosing negative examples that don't contribute, you're really wasting time. And I want to give a shout out to Jeremy Jordan, who's coached me through some of this, or handed me some references and things in particular. So this is from 2017, but I'm trying to catch up with the rest of the world. This is from 2017. This paper by Chao Yan Wu and a group from Austin and Amazon This is a great paper in describing how these um, metric losses and contrastive losses and triplet networks and so forth, pardon me, how they work. And the paper is really almost like a tutorial on the history of the field. If you read this, so a lot of papers will just have related work and they'll just kind of list off a bunch of things. And yeah, you'll see, if you notice this green text, they are listing off a lot of things. But in my opinion, they did a really good job of motivating, here's this scheme, and then the problems with that are this, and so you do this, and then you end up with that. It's very readable. So I found it very helpful. And then they end up going on to their own way of doing things, of sampling stuff. And so again, just want to caution you that this thing I wrote is a toy model. It's not even, I say, a loss, like a contrastive loss. It's not actually computing a loss function. Nowhere is there a loss function in my little JavaScript code, and there's no autograd or any of that, but it's like unto those loss functions. So yeah, sampling matters in deep embedding learning. I'll put a link to that goes with this post, right? And so the motivation for this, I mentioned this in my other posts, right? You see these contrastive loss systems that are showing up in a lot of places. And so, for example, right, CLIP from OpenAI, the CL part stands for contrastive loss. I'm in the audio world, and so the group in Barcelona, a paper with Eduardo Fonseca about unsupervised contrastive learning of sound event representations. And I just kept seeing the contrastive loss everywhere. And some of you may have noticed the explosion of AI art, like the background here, right, that was created by hooking up CLIP with a VQGAN model, or previously other models have used other things, right? With OpenAI, they hooked it up with DALL-E. And just to shout out, people at Hugging Face and Gradio have set up a demo that you guys can run here if you want to try out the VQGAN plus CLIP, and you type in your text prompt, right? And so what it's doing, right, you've got some embedding of the words, so they're all getting mapped to a particular set of points in space, and then you've got a an embedding of this image, essentially. And so there's an image describer that looks at this image and generates some text, and we try to get it through gradient descent to get it so that the generated caption matches with the text that's input. And of course, these metric embedding methods have been around for quite a while, and notably like Word2Vec, right, where we take our words, and you might start off using words in a vocabulary, like in natural language processing, as individual one-hot vectors, and that's just not feasible if you've got thousands and thousands of words. So you reduce the dimensionality of that one-hot space by embedding it into some smaller set of dimensions, and these become word vectors, right? And then you can see if you can do algebra with the word vectors, and there are a lot of results about the word vector. So that's been around for a while, and so it's really quite similar, right? We're taking something, we're embedding it into another space, and then imposing certain restrictions so that hopefully things that are supposed to be similar to each other end up close together, and things that are supposed to be dissimilar are far away from each other. Now, one other mode that I made in this thing was, let me turn this stuff off. We'll zoom in a little bit. I added a mode, yeah, attract only. So in this mode, there's no repulsion. And so here, I'll just change this, and let me run this. And what you'll notice is, oh, hold on, the constant. Yeah, I'm not actually a huge fan of constant loss. Let me do linear gradient. Okay, and we run this, all right, notice, okay, I'm at maximum zoom right now. All the points that are supposed to be similar to each other have actually collapsed to single points. So it's kind of, yeah, and then it rescales at the very end. So it's attract only, and then it rescales, so you can kind of see things. So each class is now a cluster that's really, really, really tight. And this is the sort of thing that was illustrated. There was a paper called SimCLR. It had Jeffrey Hinton's name on it. A number of people have written about this. And yeah, simple framework for contrastive loss learning, contrastive learning of visual representations. Ting Chen So the people in Jeffrey Hinton, and in this case, we're mapping into a space where they didn't use any negative examples at all. The negative examples can be hard enough that, yeah, you can see this kind of picture here, where we're going to take our points, and they actually do a thing where they map into another representation, and then they do the contrastive loss in this other representation. And their idea was you cut that off, and what you're left with before that is your embedding vectors that you use for other downstream tasks. And this is the sort of thing that was copied by Fonseca et al. For their audio, was this scheme that I've termed AttractOnly. And so that's in there well, and you see it really does a good job with clustering. But one thing it doesn't guarantee that points that are supposed to be dissimilar are some known distance away. I'm trying to find some example where, let me do like 100 classes, and we'll train this model. It's possible that you can have dissimilar things that end up close to each other in 3D, but as we go to really high dimensionality, the chances of things overlapping or even being close to each other gets pretty small. Right? But even if that was the case, so you may say, well, what's the, okay, yeah, here are a couple, there's a dark blue and sort of a greenish aqua point that are pretty close together. And you may say, well, all right, what's the point of that? Because let's say you wanted to use this as a few shot classifier where you send in various examples of something. And if they end up close enough to each other, you say, you do kind of a nearest neighbors kind of measurement. What is this most like unto? And if the model can't distinguish between things that your new input is supposed to be similar to or dissimilar to, maybe that's not a good idea. But that's not, you don't have to use this for that. You know, there are a lot of different methods and they don't all go with the best example. In this case, one of the things that we get through these representations, so these are formed the way that we form in the SimCLR idea. You take, let's say, an image, okay, and then for the positive example, you take that same image and you create an augmented version of that image, augmented through changing the colors, the contrast, blocking out some points, doing any kind of transformation that to a human being preserves the semantic content of whatever this image is, whether it's supposed to be an animal or something else, right? So you end up with two different versions of the same thing. And so this embedding method, as it learns, it essentially learns augmentation. It learns to discard all the stuff that doesn't matter. And so this kind of embedding can actually serve as a proxy for augmentation for downstream tasks. So if you've already got a model that's been trained on a set of augmentations, then you could hook up this kind of embedding on the front end of your model that's going to do some other things with images. And again, the nice thing about these embedding methods is if you train them on enough data, new classes and new things that the model's never seen before end up getting mapped to their own kind of region of space in a good way. And a proof of that concept kind of working was with Clip, right? Where they trained it in a supervised manner on the whole internet, so to speak, right? And then it still ended up getting state of the art on image classification in ImageNet. So it's a really powerful method. And so with this SimCLR option, then you've got a way, I lost my page, of having this kind of proxy for your augmentation for your downstream tasks. In a similar way to, I lost my word to vec, or, glove was another option for word embeddings. I'll put some links down below on these things where you take these embeddings and then that's kind of the first thing in your network, and then you do other operations with it later on. Okay, so I know I talk kind of fast, but this was a blog post that I was just never getting around to writing. I was going to write all this out and then tell you to go up and click on buttons and change them. And really the way to learn this is just to kind of mess around with it. So let me just say, caveat, I'm kind of learning as I go with this stuff, reading papers, and I would really welcome anybody with greater expertise offering, particularly if I said something wrong. But I think I'll cut it off there. All right. Thanks for watching. And I think for other blog posts, I'll probably write things out. Thanks.